Alright, today I'm going to be talking about the sum from n equals 2 to infinity of negative 1 to the n, so it's alternating, and then times natural log of 1 minus 1 over n. I'm just going to start out by writing out the first few terms. Natural log of 1 minus 1 over 2, and hopefully this will make the next step a little bit more clear. So we have 1 minus 1 over 4, and then minus natural log of 1 minus 1 over 5, and so on. So recall this fact here. Where if a and b are positive real numbers, this holds true. So I'm just going to apply that here with each of these consecutive pairs forever and ever. So here I'll get natural log of 1 minus 1 half over 1 minus 1 third, and then I'll add this next one, natural log of 1 minus 1 fourth over 1 minus 1 fifth, and we'll do this forever. So we can write this again as an infinite sum from n equals 1 to infinity of natural log of 1 minus 1 over 2n over 1 minus 1 over 2n plus 1. And just to let this soak in, let's look at what these terms are. So down here we have 2n, so we have 2, 4, 6, 8, and so on. So we see 2, 4 here. And then in the bottom we just have 1 greater than what's up here. So we have 3 when we have 2, and then we have 5 when we have 4. So this is even numbers, this is odd numbers, forever. Right, now using another property of logarithms, this one, which is actually basically the same as the previous one, but just going case by case makes things a little bit more simple. We have the sum of logarithms is a logarithm of a product. And this is just for when you have 2, but you can pretty much use this to show that it holds for infinite summations, assuming everything's nice, which is a really vague way of saying I don't feel like figuring out exactly when that's true, but okay. So we can turn this into the natural log of this infinite product from n equals 1 to infinity of 1 minus 1 over 2n over 1 minus 1 over 2n plus 1. Alright, now I'm just going to take a look at this inside and try to simplify it. I'm going to multiply the top and bottom by 2n plus 1, so we get 2n plus 1 minus 2n plus 1 over 2n. I'm going quickly here because if you understand the rest of this, this should all make sense. But, okay, yeah, further, 2n plus 1 minus 1 minus 1 over 2n over 2n. This leaves us with this. Multiply top and bottom by 2n, and you can get 4n squared minus 1 over 4n squared. Now we can rewrite our summation as the following. Natural log of the product from n equals 1 to infinity of 4n squared minus 1 over 4n squared. And I'll rewrite this as 1 over this product from n equals 1 to infinity 4n squared over 4n squared minus 1. I didn't motivate this very well. And by the way, this is allowed because we can see just by inspection that this product is non-zero. Right, but here's the punchline. This here is a famous product, and you might recognize it. It's called the Wallace product. And it states that this is equivalent to pi over 2. So now we can write this as natural log of 1 over pi over 2 just by plugging in that equivalence, and you get natural log of 2 over pi. So this gets us a very nice, concise little thing that answers the summation here. Just recalling the original summation, and you can write it as this Or if you want pi in the numerator, you can also write this. This is an equivalent statement. That's the final answer, and I think it's very interesting how pi shows up in here. Thank you for listening.